Okay, great. Okay, our next speaker is Mukund Gupta, who will speak about ocean sea ice interactions at the flow scale.
Okay, well, thanks everyone for inviting me to speak here. And so yeah, today I'm going to talk about ocean sea ice interactions at the flow scale. This is work that I've done with my postdoc host at CALTECH, Andy Thompson. And this is work also, this is part of the ONR movie project that's been running for about 2.5 years now. And really the motivation for this work, the prime question that I'm trying to go after is how do ocean eddies affect the flows that are in the marginal ice zones, and how in response these flows affect ocean turbulence underneath them. And so as a motivation for this, here's an image of a marginal ice zone in the east of Greenland, taken from the NASA MODIS satellite data. And here you can see the presence of these swirling filaments and eddies at the margins of the ice. And you can see them shaping the patterns of sea ice flows as they move around in the marginal ice zone. And really the scales of these filaments and eddies are on the order of 1 to 10 kilometers in these kinds of polar regions. And this is an overlap with the biggest flow sizes that one sees in those regions. And it's really the interactions at these scales that are going to be of interest in this talk. Here's another set of images taken here from Baffin Bay. And here I'm trying to illustrate the transition from spring to summer that occurs in this particular region. And as we saw in a lot of earlier talks, this transition from spring to summer is particularly important, not only for sea ice, but for climate as a whole. If it happens very quickly, we have a longer summer season, which warms the ocean more, and then can influence the whole seasonal cycle of sea ice that occurs in the following year, for example. It can also affect processes in the oceans and in the atmosphere as well. So understanding the rate at which this happens is really of importance. And you can see that the process through which this happens is not straightforward. We go from this broken up but still a highly concentrated field of sea ice flows to a progressively more loose sea ice pack with individual flows having the space to move around and get affected by ocean and atmospheric variability. So what we're going to try and do here is try to understand the processes that affect this transition and particularly the melt of these sea ice flows. This is representing some of the work that Chris talked about earlier today from his 2016 paper. And this is some really nice work which essentially showed that bigger flows can melt slower than smaller flows for the same sea ice area. This is a figure that we saw earlier today, and it shows how in configurations where the sea ice flows were constrained to remain at the same place, but were subjected to the same forcing, melted faster when they were distributed over smaller flows. And one of the main mechanisms that influenced the melt rate of these flows was the development of these eddies at the periphery of the flows that was generated through instabilities related to sea ice melt. So essentially, as the sea ice melts, it drops some fresh water underneath the ice, and this becomes unstable because the waters that are at the periphery are denser, and so they tend to create what's called baroclinic instability, generating these eddies that have particular scales. And this is a particularly important mechanism in controlling the rate at which these flows can receive heat from the open ocean. But the question becomes now, how does mechanical coupling affect these processes? In these experiments that were shown here, the flows were constrained to remain static, but obviously we're generating a lot of motion through these instabilities now. And then secondly, what is the effect of winds? There was no wind forcing in those experiments. And so we know that winds are going to probably play an important role. And finally, can we develop simple scaling laws to predict some of these melt rates? So to address some of these questions, I've been working on a coupled ocean sea ice model over the last couple of years. And so on the ocean side, I've been using this new model developed as part of this CLIMA project, the Climate Model Alliance, which is a collaboration between MIT and CALTECH, essentially to develop a new climate model. It makes use of a new programming language called Julia, which can be easily adapted to GPU architecture, for example. And this is what I use over here. The dynamical core is based on the MIT GCM, which solves the Boussinesq equations. And I've used it in this LES configuration where I have 250 meters of horizontal resolution. I have a domain size of about 32 kilometers. And in the vertical, I use 160 meters of ocean depth and vertical grid spacing of 2.5 meters. I use nonlinear equation of state, which is important at these poles. And I use a doubly periodic domain. I start my simulations with Arctic-like stratification, which is salinity dominated. And I have a temperature inversion, which is typical of these polar regions. So we have cold water above warm ones. And I start with a quiescent fluid. On the sea ice side, I use a much simpler representation. So I have this shaped floes, which can interact, so they can collide with each other. And for that, I use rheology from Herman 2016. And in terms of the melting, I use a very simple one-layer basal melt, which assumes pure melt conditions. And so there's no lateral melt representation here, and there's no breakage. So the flow radius remains the same, but its thickness can vary according to the melt rate. So some of the governing equations. So in terms of the heat equation, it's very simple. The flow thickness is affected by short wave flux and long wave flux from the atmosphere, and you also have an oceanic heat flux. In terms of the momentum, we have a linear translational momentum equation, which is dominated by oceanic stress as well as atmospheric stress. We do have Coriolis and collision terms, but in the configuration that I'm going to talk about today, the collisions particularly don't play a strong role. And we have similar equation for the rotational component of the sea ice flow. So all of these linear stresses are accompanied with torques. And then there's obviously a matching to be done here between the Lagrangian framework of these flows and the Eulerian grid of the ocean model. And to achieve that, I just do a grid refinement very close to the flows for each flow, and I match regions which are completely ice covered versus those which are not to the ocean grid, and I calculate a sea ice fraction, and I apply my equations as they're written here. So here's the first simulation that I ran with this model. It's a very simple one in the sense that I just have one big flow at the center of the domain, and I've constrained it to remain stationary at the center of the domain. So this is just to give you a feel of what one expects in terms of the oceanography of this. So we start by having a solar forcing applied to the model. So it starts to melt the ice, and as the ice melts, we develop this fresh water all around. So that's the second panel. And we also have colder waters at the center of the flow compared to the open water. And we develop these eddies and circulations which span the mixed layer depth of the ocean, as illustrated in the third panel. And one of the key things that we observe here is that so the line shadings that I've shown over here represent the vorticity of the ocean. So essentially the red lines are cyclonic features of the ocean, and the blue lines are anticyclonic. And we notice a strong correlation. We see that the warmer waters tend to be cyclonic, whereas the cold waters tend to be anticyclonic. And this is something that we can reason quite well from just pure oceanography theory. It's basically the melt dumps fresh water, which pushes isopycnals down, and so creates an anticyclonic circulation at the surface. And so what we're seeing essentially, it's coming back to the idea put forth by Chris and collaborators, is that warm cyclonic features are responsible for carrying heat towards the cold anticyclonic center of the flow. So I'll just show a movie of this process happening. So the leftmost simulation over here is the one I've just shown. And the next two are corresponding simulations with the same sea ice area, but distributed over smaller and smaller flows. So you'll see first, and I'm plotting ocean vorticity, sorry, normalized by the Coriolis parameter. And so you'll see the development of these eddies, which tends to happen a bit quicker for the smaller flows. And you'll also notice that the scale of these eddies differs between each of these simulations. We'll talk about that a bit more later. And so when these flows pop out, that means they've completely melted out. So if I look at some statistics from this set of fronts, we essentially recover the results that were presented in the Horvath et al. Paper, in that in simulations with smaller flows, the ice completely melts away much faster than when we have a single big flow. In terms of actually looking into the details of the melt rate, that's what I do on the right-hand figure. So we start with a very small melt rate, essentially, but it shoots up after a certain point, and that corresponds essentially to the instability timescale, so the time it takes for these eddies to develop, which is quicker for smaller flows compared to the large ones. And this contributes to the differences in the timing of the overall melt. So moving on from these results, we'll now introduce mechanical coupling. So we have a non-zero drag coefficient now. And so these flows are now going to be able to move in response to the oceanic currents. So they first start with a very regular motion, but as randomness settles in, we'll see the motion of these flows also being more random. And I'll just pause. I'll just like try and pause it somewhere if I can. Sorry. Yeah, this is a pretty good spot. Okay. So I just want to point out a couple of things from the simulation. So the green line that's at the center of these flows represents the rotation. And when it's colored in green, it means anticyclonic circulation. And when it's colored in red, it means cyclonic. And you'll notice that there's no flow that's red. So all of them are rotating in an anticyclonic sense. So what we're seeing really is that these flows are being trapped by anticyclonic features. And as we saw before, anticyclonic features tend to be colder than cyclonic features. So that's something to note, and that's consistent across all scales here. And so we'll expect different melt rates for these flows now that they've been coupled to the ocean, and that's something I'll show a little bit later. So to try and understand the mechanism behind this trapping, I won't go into all the details, but this is just a summary of what we found. So there's a different mechanism that occurs for small flows compared to large flows. So by small and large, I refer to the flow radius compared to the typical size of eddies in that simulation. So when the flows are much smaller or somewhat smaller than the eddy size, we see that these flows are coupled through a translational process. So essentially, you have originally an anticyclonic circulation that develops underneath the flow. And as this anticyclonic circulation moves around, the flows just follow it around. This is a little bit different when the flows are much bigger than the eddies that they generate. In this case, it's actually the rotational motion of the flow which pushes away preferentially the cyclonic features. And so it acts a little bit like a windshield wiper, just pushing away the cyclonic features, and you just remain with weakly anticyclonic rotation. Finally, I'll talk a bit about the effect of wind forcing. So here, I'm going to apply winds in a periodic sense with, I think, a time scale of about 20 days. And you're going to see these flows moving around. And the direction of the wind is from southwest to northeast. And so the flows are going to move in the horizontal direction, in the x direction, because there's a turning angle. So on the left is vorticity, and on the right is the surface temperature. And what we're seeing is two things. The first is we're not really seeing the development of eddies anymore. And that's principally because you're distributing the salinity forcing around. So you don't really have those gradients that the instabilities can develop on. The second thing is that you're pushing the flows into warmer waters just through the effect of winds. So that's also going to accelerate the melt rate of these flows. And you can see that in a statistical sense. So when the winds pick up, either at a crest or a peak, the melt rate increases almost instantaneously, almost. Yeah, there's a slight amount of lag, but the phases match pretty well. Okay, so here's a summary of a couple of things that I've talked about today. So we saw that the flow size has a strong effect on the melt rate. This is something that was talked about in previous work, but we've recovered that result. Secondly, we saw that the ice ocean drag has an important effect on the melt rates. And thirdly, we saw that winds also have an effect on the melt rates. So now going forward, what we'd like to is sort of build a framework that incorporates all these three different effects and see whether we can understand them in a more intuitive sense, and see if whether a simpler model can represent these processes. Okay, so to do that, what we did was to consider a control volume that's right underneath the flow with depth that corresponds to approximately the Ekman layer depth, or it's a depth basically that is effective in terms of transferring heat from the ocean to the sea ice flow. So that's the control volume in black. And we're going to consider an equation that controls the evolution of that temperature of that box. So there's a tendency term, and then there's an ice ocean heat exchange term, which is controlled by this QIO parameter, the heat exchange parameter. And then there's, in the lateral direction, there's a stirring term, which is controlled by kappa E, that represents an eddy diffusivity term. And the final term is an advective heat flux. And that's basically an advection in the reference frame when you're moving and following the flow. And then we're going to combine this with an equation that just gives us the melt rate due to the oceanic heat fluxes. For this purpose, we're ignoring the atmospheric heat fluxes because they're the same in all the simulations. And combining these two equations and assuming a steady state temperature in the first one, we can come up with an equation that tells us the melt rate of the sea ice, which depends on these two terms, where we have the first term being the eddy diffusivity, so the eddy diffusive term, and then the second is the advective term, which depends on the difference between the ice and ocean velocities. We're trying to apply this equation to some limiting cases, like the ones that we've seen before. So we're going to start by considering cases where one can ignore the advective contribution and just look at the diffusivity. So by using mixing length theory, we can just approximate this diffusivity by a characteristic mixing length and an eddy velocity. So to get appropriate parameters for those, we can turn to looking at some snapshots of the simulation. And we can see that essentially the size of eddies that we have in our simulations tends to increase quite linearly with the flow size. So we can choose our F, the flow radius, as a representative mixing length. And for the eddy velocity, we just take the square root of the eddy kinetic energy, which is quite easy to calculate the domain. So putting that together and using traditional sort of scalings for other parameters, we can get this, scaling law, essentially an approximation for the melt rate that one expects from these processes. And we apply this to the simulations that I've shown you. We're running a few more for different flow radii. And it does really well, actually, by using appropriate parameter values for all the other terms. It's not as great for smaller flows, slightly overestimating the melt rate there, but I think probably in this case, the steady state approximation is not quite as tenable because the flows melt rather quickly and it's a more of a transient process. But other than that, it does pretty well. Now we're going to look at the effect of ice ocean drag on sea ice melt rates. So we're going to consider the full equation. And really the important term here is the second one. It's that delta U times dTdr. So again, applying some traditional scaling law methodology here, we come up with a melt rate which depends on the stirring contribution augmented by the advective term. So what we do is we diagnose delta U for each of the scenarios that we have, and we can again plug in that value to come up with an estimate from that scaling law. And we again see that it matches quite well with the simulated melt rates that we see. Just one thing to point out, so the delta U that we use is slightly different for the small flow case, which is the top one, compared to the large flow case, which is the bottom one, so 2 and 8 kilometers respectively. As we had seen before, in the small flow case, it's really the translational velocities that matter. So the delta U is simply the centroid velocities for each, for the ice, and just the ocean velocity averaged over the flow. But for the large flow case, the delta U is defined slightly differently. It's essentially the velocity of the flow at the edge. So it's the rotation rate times the flow radius, and the flow and the ocean velocity at the periphery of the flow. And we can also come up with some threshold drag coefficients. So if you notice in those curves, as we increase the drag coefficient, the melt rate decreases, and that's because we're starting to couple more to these cold anticyclonic features. But at some point, the curves tail off, and there's no more effect of the drag coefficient. And that's because we've kind of saturated that mechanism, and the flows are perfectly coupled almost to these cold features. And we can come up with some theoretical values for where that threshold should happen, which I've shown over here. And they also match up pretty well with what we see in the simulations. And finally, I want to apply this to the case where we have winds applied to the simulations. And in this case, we can ignore the diffusive term, and we're just left with the advection. Again, we apply some scaling methodology to come up with an expression for the melt rate. And critically here, we have to turn this delta U into something that depends on the wind speed. And we do that by using a simple Ekman layer theory. And so going through the algebra, we essentially find the melt rate to depend on this non-dimensional parameter called mu w, which depends itself on the flow velocity. And this mu w parameter represents the strength of the advective heat flux over the vertical exchange to the ice. And so to test this, we run some more simulations with different values of wind speed, different values of the flow radius, and different values of the ice ocean drag coefficient represented over here. And when we plot them all against the non-dimensional parameter, they line up onto a curve which is given by the scaling law for appropriate parameter values. So again, we see that the scaling law does pretty well. The only exception to this is when we turn towards really low values of mu w, which is also low values of the velocity of the atmosphere, then the scaling law would actually predict that the melt rate goes to 0, but in fact it doesn't, and that's because the melt rate is augmented by the diffusive process, which we've ignored in this framework. So in summary, we find that there is 3 different regimes of flow melt that we can distinguish in our simulations. So the first one is the panel on the top left, which represents low wind and small flows scenarios. So in this case, we saw that the melt rate was limited by the translational motion of sea ice flows. And the dotted line represents the threshold at which this mechanism occurs. So below that line, we expect this mechanism to occur, and above that line, it's not as strong anymore. The flows are perfectly coupled. And on the panel on the right, we see essentially the same thing, but for large flows. And in this case, the overall melt rate is significantly lower than in small flow cases. And that's because of the fact that eddies are less effective at carrying heat towards these large flows. And finally, the third panel, which is the one on the bottom, represents the third regime, which is when winds are significant enough to affect the flow melt rates. And we again see that there's a critical velocity above which this mechanism occurs, which is plotted in the dotted line. And beyond that, we can't accelerate the flow melt rates further. So in summary, we explored the effects of mainly 3 different parameters on the flow melt rates. So the flow radius, the ice-ocean drag coefficient, and the velocity of the atmosphere, or the wind velocity. We identified new coupled mechanisms that influence flow melt rates. And we developed scaling laws for these flow melt rates, which largely depend on measurable quantities, such as the flow radius, the wind velocity, and the temperature difference between open ocean and under ice. And so just a bit of outlook for what might come next from this. What is the importance of breakage? Our flows don't break at all. Surely that must have an impact on this transition. Right now, in all our simulations, the flows were the same size, but what if you mix small and large flows together? What happens then? This is something that we've started exploring with these kinds of simulations, and we're seeing some interesting things, but they've raised more questions than they've answered so far. And then here, in all our simulations, the turbulence that was generated was just through the sea ice melt itself. But we know that in polar regions, there are mesoscale eddies, like in everywhere else in the ocean, which are not generated by sea ice melt. And those mesoscale eddies are not just spanning the mixed layer depth, but they're spanning the whole water column. So it would be interesting to see what is the effect of these larger scale features of the ocean on the processes that we have, and how they affect the submissive scales that we see here. So with that, I'll thank everyone.
Great, thanks very much. Any questions? Danny.
Well, I think it's just brilliant what you've presented. So fantastic work. It's really a quality piece of work. I'm very excited by this. I guess I'll just add to your 6, 7, 8, 9, 10. Okay. One thing which seems a logical thing to include would perhaps be the effect of waves, ocean waves. You include the effect of wind speeds, but waves are probably going to affect that just as much as anything else you've listed. Okay. So typical wind speeds, would we find ourselves in the wind-dominated regime?
That's a good question. So actually, yeah, we can see it here. So it depends on the flow size. So if you have flows that are on the order of 0.5 to 1 kilometers, if you look at the bottom panel, then you only need about 1 meters per second wind speeds to really affect the flow melt rates.
Okay.
But if you have really large flows, then you need stronger winds to affect them. So for example, if you have an 8-kilometer flow radius, then you need 10 meters per second winds.
Okay, the really small flows is what you're actually interested in. So 10 meters, 50 meters is probably the exciting area.
Right.
Yeah.
Any other?
Hello, thank you for your talk. Oh. I'm sorry if it's a bit out of context or it's a nonsense, my question, but do you think that a dense packing of flows will have an effect over the eddies underneath and the thermodynamical phenomenon that you study?
Yeah, certainly they will. You can kind of see it in this image already a little bit. We see that when we pack the ice more strongly, then it leaves less space essentially for instabilities to develop. So that makes weaker eddies. In addition to that, the rubbing effect from eddies towards the ice becomes more important. It may be also underestimated in this model because we have circular flows, so the contact is smooth. Although we do have parameterization for energy loss through collisions and through tangential motions, they may be underestimating how much energy loss there is from ocean sea ice interactions, frictional interactions. So yeah, I think that's something that we'd like to explore going forward.
There's a question in the chat. Hi Mukund, nice talk. I wonder what is your guess how often we are in case 1 and 2 versus case 3, or phrased in another way, how often do you expect there are low winds? And this is from Mom Hell.
Yeah, it's a good question. So the way I've defined the wind speed as well over here is through a period of 20 days. So there are periods where the winds dip down in these simulations as well. We're often in cases where there's high enough frequency of winds, which can exceed 10 meters or 15 meters per second in the Arctic. But it'd be interesting to know how much persistence we need these winds to last for, really, to have a strong effect. The other thing to consider is that we are often in situations where there are large-scale currents that are superimposed onto this. And so kind of looking at the coupling between those wind events as well as the larger scale transport of these flows would be an important step to answer that question, I think.
I was wondering if your ice was levitating, and if you thought your ice was embedded, do you think it would have an impact on those results?
Yeah, it is levitating. I guess we're representing that effect just through the parameterization of the ice-ocean heat exchange. I don't know if really we'll see much of a difference if we resolve the depth at which the flows actually go down to, except when we really start thinking about irregular flows in terms of their vertical representation, like keels, etc., sails and keels. I don't think we're at a resolution where we can really resolve this very small scale turbulence that would occur through these interactions. We have 250 meters resolution in the horizontal, for example. So we do have to parameterize the effect of these small scales right now. But yeah, I think if we ever move to these really high resolutions, then we'll have to start thinking about that.
I'd like to add just one really quick thing. This is fascinating to me, and it's kind of new to me in terms of what all the motion and turbulence and eddies that are going on as you're melting. But this coincides, the timing coincides when the algae is coming out, the krill are happening, and all this biological activity is ramping up. And I'm curious if this motion and this turbulence is connected with any transport of biological critters and so on, and plays a role in helping to enhance things, or?
That's a great question. One of the things that's really important is the vertical velocity of the ocean. And submesoscales are typically associated with very large vertical velocities. We actually don't see that happening in those simulations. And it's possibly because we're not resolving some of the processes that give rise to very large vertical velocities. Yes. But yes, in our more sophisticated simulations, I think we'll be seeing more of that. And I think it'll be really interesting also to think about how the light field evolves as the ice melts. Yeah.
Thanks very much.